unless somebody's got a problem that just jumps off the page.
I've got a question about, in the OneNote, it said that for the Gaussian homework that the quiz was going to be based on one of those problems. Is that for next
Not
week?
Gaussian. The quiz is based on, if you look, the way it stated it, I took your suggestion actually to use this book and I gave you additional problems.
Yeah.
Go with me? So that's what I was trying to do, is get you to, that's what it didn't have to do, the Gaussian stuff, the quiz is not gonna be on Gaussian.
Okay.
It's gonna be on stuff that I gave you for homework, that is relative, it has to do with moments and things like this.
Yeah,
All
I
right.
kind of stressed this out when we glanced over it, and you're like, I hear this happening, he didn't really got
Wasn't that clear? I gave you some problems in this book, right?
Yeah, you did.
And I said, one of these is gonna be what the quiz is based on.
Okay.
Yeah,
This
but
is
it
not
also
Gaussian.
had the 2.5 stuff from the other book on the same page.
Yeah.
And it said one of these problems is going to be on the
Well, I got you to actually do that. All right, well, here's my goal, all right, so I'm gonna start with, unless somebody has one that jumps off at them, in section 4, 2-4 in the Cooper book. What am I doing? I'm gonna try to do, 2-4.3 and, 2-4.4, so, actually, let's see. We'll do it this way. You're here? Here, you can take that, and you can take that. All right. So 2-4 point, I think it's point 3 is the one I want to start with. So go ahead and can you give that? I think these are all basically the same type of problem. They have different, you need to do different things because of the way it's set up. But go ahead.
2-4-3. Yeah.
This is one of the assignments.
Dadgum, man, there's a lot of 2 dashes. Okay.
No, these are problems in the back of the book.
These are
Sorry, problems at the end of the chapter.
yes, sir. Well, there's like 2-8, 2-9, 2-4.
4-3. There you go.
Okay. So a random variable y is a probability density function of the form f of y equals ky between 0 and 6.
Did we do this one, by the way?
Yeah.
Entirely? All right.
Say that again.
Forget it. We did this one. 2-4.4.
Okay. Okay, yeah, this is a new one. A power supply has 5 intermediate.
Oh, this is an interesting one. Let me just do this. So you got 5 loads. And each one of these uses 10 watts when they're on. This is an interesting one. But they're all on with a probability of just 1/4, basically 25%. Y'all with me on this? And they're all connected together. All right, go ahead.
Find the mean value of the power required by the loads.
Now, usually when you think of mean value, you think of integrating a probability density function times whatever the density function is relative to, right? Or this is discrete, right? Do y'all agree with this? So when we're talking about the average value of a discrete system, and they want the power, right? Or the mean value of the power
Mean
consumed.
value.
So this is the estimated value, and I'll just call it of P. So what that's going to be is equal to, and it's a sum, and this is going to be of the power of each one of these. I'll call it P of I times the density function P of I. These are really just going to be, if you think about these things, each one of these is separate. They're discrete. Y'all follow me? Did y'all do this one? It's an interesting problem. So here I goes from 1 to 5. So this really is just going to sum them up. So it's 10 times 1/4, and each one is identical, and that's times 5. So this should be 12.5 watts is the average power. Do you agree with that? Now, the only thing I'm doing here is just showing you we could write this out as what? This has a density function of 1/4, this 1/4, this 1/4, and we could actually draw it out. And then when we take a look at the average value of this, because they each consume 10 watts, it's 10 times this, 10 times this, plus 10 times this, 10 times. So you get the idea. Do you all agree with that? Does this problem make sense to you? Okay. Next, they ask for what?
Find the variance of the power required by loads.
Okay. Variance itself is what? Well, you could, if we wanted this, if you think about this, couldn't we say this is equal to x squared bar minus x bar squared, right? We could do, did you all do it that way? I don't remember how the book did.
Yeah.
Or you could get, since we know that that's the mean value, we could literally take x minus 12.5, right? Take that and then multiply by each one of those probability density functions and just do it this way. So if we do the x estimated value of x squared, all right, here's what I'm going to do. So that's x estimated value, and I'm going to call each one of these, I don't remember how he does it in his book, but this is x1, x2, x3, x4, and x5, where x represents the power being used by that load. Y'all follow me? And they're assumed independent, I believe he says that in there. So this is, now when you did this, I don't remember how he did it exactly. When you look at this, really we're going to have this. It's the expected value of x1 plus x2 plus x3 plus x4 plus x5 squared. Do you all agree with that? Just write it down, right? If you look at this, each one of these has an identical power consumption, an identical actual probability of being on. So there's nothing where we have a large mess of terms we have to expand this thing on. The way you can write this is the expected value of, now if there's 5 variables, right? You know that x1 is going to, if you take this and write it out again, maybe I'll do this just to show my point. Many of you probably see this plus x5, and then we have x1 plus x2 plus x3 plus x4 plus x5. If I multiply this through, I'm going to have x1 squared one time. And then I'm going to have x1 times x2, x3, x4, x5, right? And then, because this will be identical to x2 times x1, x3, x4, x5 in terms of the actual probability of that occurring, or the mean value, or the mean squared value of that, what I can do is say, well, x, the first terms, there's 5 of them, occurs 5 times. So it's 5 times the probability, or times the actual squared value of xi. Does everybody understand the rationale? I'm not explaining it quite the way I want. Because this x1 is going to multiply x1, right? So you have x1 squared. x2 times x2, x2 squared. But this will occur 5 times where the same indice is both in the, I guess, in the first term and the second. Do you all agree with that? Mm-hmm. Now, for the other ones, if you look at this, x1 has to multiply all this, or xi has to multiply all that, and that's going to occur 5 times as well. Do you agree with that? You follow me? So I'm going to have plus 5, and this is going to be times xi, and then you got all these other ones, and these you might as well just call them xj. And actually, put it this way. There's going to be 4 of those, 4 times xj. And that really is going to be the expected value. I hope I'm making my point. I'm not saying it quite the way I'd like to. But do you understand that this is really one of these things where well, we're going to keep working with this one. This is one of those things where the x represents the power xi, the power consumed by one of these, and xj would be something other than xi. That's all I'm trying to say, and I'm not doing very good. So when we do this, right, you can break that out. That's the expected value of 5 times xi squared plus 5 times 4 is 20 times the expected value of xi, xj. I hope I'm saying that right. Does that make sense to everybody? Okay. We've got, if you look at this, because these two are independent, right? This is just going to be plus 20 times the expected value of xi expected is just going to be x bar squared. You agree with that? Because xi and xj are independent, right? So if you have independent variables, it's the probability of first times the probability of second. Y'all remember this? Am I making myself clear? Sometimes I'm struggling for words to actually explain this. But what I'm really trying to say is they're discrete. So probability of A times probability of AB is probability of A times probability of A, or probability of A intersect B. Does that make sense to everybody? Can you all tell me we could draw Venns of this thing? Now what about this one? Well, that's the expected value of just the first value variable squared, right? And what is that going to be? Think about it. Let's just think. The expected value of the power consumption squared of the first one. You all with me? So it's going to be expected value of xi, but it's squared times probability of I. Just think about this. Well, the value of x is 10 watts when it's on, correct? Maybe I didn't state that clearly. Do you agree with this? So if I square that, I get 100. Now this is discrete, it's meant to be very simple, but sometimes it's oversimplified. Now I need the probability of that occurring, which is 1/4. So this is 25. Do you agree with that? Now that's the expected value of xi squared right here. And I have 5 times that, right? So this should be 5 times 25. Yeah, that's right. Plus 20 times x squared. Let's just see. I don't remember exactly what the answer is. So that's going to be 125 plus 20 times 12.5. What do you get for that? I don't remember. I didn't do this one last night. I did it a while ago.
No, that's, the answer is 93.75 for the whole problem.
No, what's this one? This is the first one, right? This is the expected value of x squared.
Yeah, it's 93.75.
For this one, is that what he asked for?
He asks for, I mean,
Wait, is that 93.7? No, it can't be. That's 125.
because we were solving for something else, right?
I know, but
This should be
we're
the
just-
final answer.
No, this is this right here. It's the mean value of x squared. He wants x minus x squared, that value.
Yeah, what do you
Alright,
get?
so
this one's
375.
375.
Say again?
375.
Did you all do this way or not? No, I'm just kidding. So now, if we have that, what he actually wants is this, right? Okay, doesn't he?
Yeah.
All right, so this one is going to be what? Well, that's the expected value of x squared, which is 375, right? Minus x bar squared, and x, where's x? 12.5 squared. What do you get for that? I think that's what he wants. I don't remember if he wants sigma or sigma squared.
That gives you 218.75.
Is that right?
But the answer here is 93.
What did he ask though? The expected value for what?
Find the variance of the power required by the loads.
Well, did we do something wrong? That's the variance, isn't it?
I think we went wrong somewhere.
Hold it, wait a second.
Because 20 times 12.5, if you work backwards, should give you the right answer. Because 250 minus 12.5 squared is 93.
Is that 375?
It should be 250.
Wait a second, but just do me a favor. 12, if you take 12 times 10, that's 120 times 2 is 240. Yeah, that's 375. Did we do something wrong here? This one. I worked this one. Hold on for a 25 should be value, mean square value of one of them. Wait a second. The average value is 2.5 for one of those, right? I mean, pardon me. So I have wait a second. I want to just make sure about this. I did this one 2 days ago, 3 days ago. When I look at this right here, that should be absolutely the right ID. Hold on. 1, 2, 3, 4, 5. 5. So this will be 5 times 25, guaranteed, plus 5 that should be 5 times 4. X bar squared. Looks like X bar. Oh, I see what it is. You know what? This is going to be, the X bar here is going to be a single value. It's going to be the average value for just one. I'm sorry about this. Not for all of them. Y'all follow me in this class? So this would be 5 times 4, and for a single one, what is that? That's 2.5. This probability is 10 watts times 1/4. So this should be 2.5. Try this one now. And this is going to be 125. Tell me what that number is. 175? 175? Is that right, class? Yes. All right. Wait a second. This should be 2.5 squared. My bad. So, my bad. Because this is going to be the mean value of xi times mean value of xj. J and I are unequal to each other. So this should be 125 plus 20, and then it should be 2.5 squared. I'm very sorry about that. Go ahead.
That's it, let's keep it. Yeah.
What's the value?
250.
250?
Mm-hmm.
Here's the problem. The xi and xj are both from one single actual power supply. I was putting the whole value, we got the mean value for the entirety. All right, that'd be a different problem. So that's that, and then we can get this right here, which is going to be 250 minus x bar squared, and x bar is, this is the actual x bar, which is 12.5 squared. Is that right?
Yeah.
Yeah.
That's right.
What is this? 93 you said?
Yeah, 93.75.
I'm very sorry about this. These are the individual values. When you take the expected value of this last term, and I better just say this, this one right here, if we take it and expand it, we have 5 times the expected value, and this would be of xi squared. Well, that's the expected value of the squared, the mean squared value on one of those power, or one of those power supplies, whatever they are, plus, and then it's going to be 20 times the expected value of xi times the expected value of xj. And let me just say this: these are individuals. They go from 1 to 5. The power supply. each one of these is x bar, which is 2.5. I'm very sorry about that. You okay with that? Is that the end of that section?
There's one more problem.
That is.
What is the next problem?
A random variable x has probability density function in the form of f of x equals ax squared.
All right, we'll do it real quick. By the way, this one's kind of a weird one. You know why? You don't have that easy ability to see how the density function maps on this one. I mean, how you can see it. That's my opinion. It's actually a big problem. All right, this is 2-4.5, is that right?
Yes, sir.
Go ahead.
So
F of x equals what?
x equals ax squared from 0 to 2. X is 0 to 2. Then there's another one, ax, that's from
Oh, ax squared from where to where?
0 to 2.
0 to 2. And then
We have ax from 2 to 3.
x greater than 2 less than 3. Go ahead.
And then you want to find the value of a.
All right, now this one's straight, right? The only thing you need to do is say, if I integrate f of x dx from minus infinity to infinity, I have to get 1. The probability density function integrated over the range of possible values has to be 1. Agreed? And if it was discrete, it would be the sum of each value of probability at the discrete point. That times the actual value. I mean, that summed up over all possible discrete points would be equal to 1. So this one is straightforward because we have two things. So we have the integral of ax squared. I didn't do this one, but it seems very straightforward. From 0 to 2 plus the integral of ax, and this is going to be from dx from 2 to 3, and this has to be 1. So here I'm going to get simply ax cubed over 3 from 0 to 2 is going to be a, and it's going to be 2 cubed over 3, plus here it's a, and then when I integrate x, I get x squared over 2, and I evaluate it from 2 to 3, so this is going to be 3 squared, or 9 minus 2 squared. And that means if that's 1, I can take and say that a, therefore, over here, I'll do it right here, is going to be equal to 1 over, and this is going to be 4/3 plus, and that's 9 minus 4 is 5, plus 5 halves. And tell me the value for a for this one, please. I didn't do this one, but
A equals 6/31.
is that the answer in the solutions, Bob? I'm pretty sure. I mean, you have to understand that
Yeah.
6/31, did you say?
Yes, sir.
Okay. Now what?
You want to find the mean
Mean.
of the random variable x.
The what?
The mean of
All right, so the mean value, the expected value of x is just going to be the integral. And this one's straight, so I'll just put it down. So it's the integral of f of x, right? And times x over the range, technically from minus infinity to infinity dx. For us, it's going to be the integral from 0 to 2. And here it's x times f of x, which is a x squared, right? And dx plus the integral of x times ax dx from 2 to 3. And that will be the mean value of x. I hope everybody's awesome. I'm trying to just put this down. If you do this, you can see only one thing happening. It's different. And that's going to be the integrations have a higher power. Instead of an x squared integral, it's an x cubed. So this one is going to be a integral of x cubed is x to the 4th over 4. So this is going to be 2 to the 4th over 4 here, because that's x cubed integration plus, and this is a, and that's going to be an x squared dx integral So that's gonna be x cubed over 3, or 3 cubed minus 2 cubed over 3. And that should give you x bar. A is 630 over 31st. Can you tell me what the answer is?
2.
Is it 2?
It's 2.
Wow. Okay. And what else do they want? Meet the expected.
Then what's the probability that, find the probability between 2 and 3.
How do you do that?
Integrate between 2 and 3.
It's going to be what? Just this one, ax, right, times dx integrated between 2 and 3, correct, class? So that part, can you all follow me on this one? Can you do this one, class? I don't want to waste time. Everybody, anybody need me to do this? You got it, bro? You good with this? All right. I'm trying not to waste too much time here, but I wanted to do a few of these. Did they ask anything else on that one? Now, I'm going to ask something. So if I wanted, hear me now, if I wanted the actual value of the variance, how would you get it? You could do it a couple ways. We got the mean value, right?
Get the mean
If I
square
want the
value.
variance, if I take the, go ahead, say it.
Get the mean square value first.
So I would go, and he's right, I would get the mean squared value by doing integrations, but now the integrations would be what? It would be a times x to the 4th, and the integral here would be ax cubed. Agreed, class? Because you're multiplying by x squared, then integrate that to get the variance. I would take that value, the expected value of that, and I'd subtract the mean value squared, and I get the variance, and the standard deviation would be the square root of that. I wanted to say that. We're going to move on. This one, I think, is straightforward. That one, I messed up. I'm sorry. All right, now I want to get into Gaussian variables before you get your quiz. Let me say one thing about Gaussian variables. It's very important to appreciate this. This is used extensively in engineering, everywhere. How many have seen Gaussian distributions in some classes? You have had to. If you had solid state physics or microelectronics, you had to talk about the distribution of, well, I don't know if you did or not, because nowadays I'm not sure. Yeah.
One of my favorite examples of Gaussian distribution is there's a picture online of the gym sacks, like the peg things.
You mean weights?
Yeah, the weights.
Yeah, where you can take a pin and get a different
yeah.
weight on the machine. Yeah.
The wear marks, it goes thicker and then thinner as they like.
So there's a mean value and it's a Gaussian
Yeah.
distribution where on the.
Yeah, it's actually really interesting.
It might be. Gaussian, anything that naturally occurs, almost. If you looked at velocity distribution of molecules in just x, the Vx component, you'll see they're Gaussian. If you look at the actual, this is kind of crazy, but in archery, say you got a bullseye 100 yards away, which is a long way, 40 yards away, and you take people and then have one guy or one say team just shoot arrows at that thing and you look where they hit. Over time, if this is a very long thing, you'll see that the actual probability density function for the actual vertical and the horizontal displacement from the bullseye fit perfectly in a Gaussian, the mean value right at the bullseye. And you get something, a Rayleigh distribution from that. If you take a look at almost anything that is naturally occurring, something that is repetitive with a large number of events occurring, samples and stuff like this, you'll see they fit very well in Gaussian. And it's an amazing type of thing. And there's something called the central limit theorem we'll talk about too. Now, these are things I'm very familiar with because I did my graduate work, I did some plasma physics and courses in plasma stuff. And they use these things and they get the mean value of velocities and they get the mean energy and they get all sorts of stuff. And you're going to see that. Do you remember when you had, I think it was chemistry probably, you remember that 3/2 kT was equal to the actual energy? Do you remember this at all? Do you know what K is, Boltzmann's constant? Do you remember that equation? No? Okay, it has to do with the energy in the gas. Okay, never mind.
It's 3 years ago. Almost.
Chemistry. Okay. Here we're gonna go with Gaussian, and I'm gonna try to make this very applied. So the Gaussian distribution, accept it as something that's based on a huge amount of observations, and it works flawlessly. So f of x for the Gaussian distribution, we put this up here, is really 1 over the square root of 2 pi. This is only in one dimension. This is sigma. Now, this is real important, star this one. That sigma is the standard deviation of only, this is important, x. You'll see why I did this. It's that, and it's going to be times exp to the minus, and this quantity is x minus x bar squared over 2 sigma squared. This is the common way to see it. Y'all with me? Now, if you look at this distribution for a second, the most likely value to occur, the thing that has the highest probability of occurring, is going to be at the mean for a Gaussian random variable. It doesn't have to be that in general, and I'll explain. I'll try to. So if this is x, and this is the density function, and this is the mean, that's where the main, the highest point is. And it will look like something, they call it a bell curve, because it looks like a bell. Y'all with me? Now, what's the height of this thing? Just think about it. Well, at the mean value, this is the mean right there. Sorry, I didn't put that. Well, the height, what's the f of x or f of x bar? Well, x bar, right, when x is x bar, it's e to the 0, which is 1, correct? Just watch this. So that means this value right here has to be 1. 1 over the square root of 2 pi sigma. Y'all with me? So here's something to note. He doesn't bring it up in the book. If I give you a diagram like that, or a plot on a test or on a quiz, and I'm not going to today, so don't worry about it. But if you look at that, you can get the value of sigma. If this is, say, 5, just work with me on this one, right? You know the square root of 2 pi, you can find sigma, right? Sigma would be 1 over the square root of 2 pi times 5, and you got sigma. Now, once you got sigma, just by looking, you also have x bar. Now you have completely and entirely defined the probability density function by an observation. You all with me? Believe it or not, that's how they do it a lot of times, when they just get a ton of measurements, it fits in a bell curve, and they just, by inspection, they get the values. Okay? All right. That's that. Now, what is the probability of x, the random variable x, being less than some specified value of x? Well, it's the integral from minus infinity to x. By the way, you need your calculators out now, because I need to, do you have a calculator? I want to make sure you know what functions on your calculator do what. I'm going to show you what I do. Now, I'm older, and I use an HP. Anybody here with an HP?
I have an
Is that an HP? That doesn't look like an HP to me. All right. That one I might be able to use. My HP is much different looking than that. Age is going to be the integral of f of x dx. You all agree with that? The density function integrated from the beginning.
What's the fancy X?
Capital X just means the random variable.
Just a capital
So it's really saying the value that the density function, if you just, what's the probability that x itself is less than or equal to the definable x, small x? I mean, that could be 5, it could be 1, it could be 0. Y'all with me? So when you do this, this is real important. This becomes equal to the integral of 1 over the square root of 2 pi sigma, and I'm just rewriting what I'm talking about there. Quantity minus quantity of x minus x bar squared over 2 sigma squared dx. And this goes from minus infinity to x. Now, in the book, and really, here's where I need you to be attentive. Take a look at your calculator. Now this is this is the density function or distribution function, so it's f of x of x. Do you agree with this, class? Here's something important about the show. And you all agree there's nothing new so far, other than the probability density function that was defined, the Gaussian. We haven't seen that yet. Well, you saw it last class, but just briefly. Now what I'm going to do is show you the way you do these calculations, and there's two ways. So the first is they talk about a function that they call, I believe, the characteristic function, but I don't remember the name. It's just this symbol with x in it. And you're going to see it's tabulated in the back of the textbook I have, and there's tables online. There's all sorts of information. I'll provide some tables in case, but your calculators do this. So just listen. This, or I'll call it u, this is defined as the integral from minus infinity to some value of u of 1 over the square root of 2 pi. They assume for this sigma 0, and the mean of u is 0. And it's going to be e to the minus u squared over 2 sigma squared. Well, sigma actually is assumed equal to 1. So it's u squared is right here. It's exp to the minus u squared over 2 du. All right? Yeah, it's going to, it's assumed it's 1. Now this is called a normalized function. They take out any skew in this. So if you look at this, and I just put it down here, if you have f of x, all right, and you want to know what it is, what you do is let u itself be equal to x, whatever value of x it is, minus x bar. Remember, this has a mean of 0, right? So I'm going to subtract off the mean value from the variable, the f of x that we have. You all with me, class? And then you simply go ahead and divide that by sigma. This is a real important point. And I'm going to do a problem. And you get something that he calls the characteristic function, I believe. And I don't remember what the book we have calls it. But it's just something that's useful for calculations because there's tons of tables. There's tables in the back of that book, Cooper and Millen. I think you have the PDF of that, right? And these, I don't remember, who has that book of mine? So in this book, and if somebody wants to look this up on the other book, what's his name? On Selleck, you can. But in this book, in the back, it's kind of a cool function. I used to have to look these up long ago. Y'all, have you had thermal yet? You're having thermal, right?
Yeah.
Do you steam tables still in there?
Yes.
God, I hated those. I hated steam tables in there. This should be mathematically available. It should, I'm sorry, like on a calculator. It shouldn't be that crazy. Don't tell the guy that. All right, this is actually called the normal probability distribution function. On your calculators, you have something called probably normal distribution or something like that. Please take a look. This is on page 432 of this book. Okay? So let me give you, now this is one part, I'm going to give you the other part. I'm going to show you how I do this. Because the way I do it, I think you'll like it. Because I know your calculators have the function. So this is, what this really is, if you look at this distribution function, instead of x, I'm on purpose going to do u here and call it f of u. And you know for f of u, you have sigma equals 1 and a mean is 0. You with me, class? So what this looks like is this. And the height of this right here will always be 1 over the square root of 2 pi. It has to be because at u equals 0, this is 1, and that's the height. It will always have the same shape. So if you want the probability, for instance, say you want the probability that x is less than some value x here. All right, and say it's a Gaussian random variable. What we do is we want this, so our first step is to get, say, u itself is equal to whatever x is minus the mean value of the actual Gaussian distribution. And you have to divide it by the standard deviation of the Gaussian distribution. This is important. Now this value you take and you simply plug it in there and you will get the value of that probability. But it's always the probability that x is less than that. You with me, class? Now, if you take this right here and say, and this is the next part is important too, I'm going to do it right here. Suppose, and please listen, suppose I don't want the probability that's less than it, suppose I want the probability that x is greater, the random variable x, than some x. So that means I want this value up here, some value of x I just arbitrarily choose, I want this. Y'all with me? Well, now they develop a function that's called the Q function. And this is tabulated, I believe, in MATLAB, and I think your calculators may have this. You can look up Markham's, M-A-R-C-U-M, Markham's, apostrophe S, Q function, capital Q. You can look it up on the internet and see about Inspiron and HP. I know HP has stuff like this, but I'll show you what this is. So the way to do this is first they define a Q function of U, and here U is equal to x minus x bar over sigma, and it's equal to the integral. Now it's the integral from U to infinity of 1 over the square root of 2 pi. Again, sigma will be assumed 1 for this, okay? And if you look at this, mu bar is 0, just as the characteristic function. I'm calling it characteristic function. And then it'll be exp to the minus u squared over sigma, over 2 du. So really, when you look at this, you can see one thing becomes real apparent, and I know this is really, and this is called a Q function. I better make it a bigger Q or something, because it's almost looking like my characteristic function. Let me do it like this way. That's a Q function. With me? That's the characteristic function. Now look, characteristic function goes from minus infinity to u. The Q function goes from u to infinity. So one thing that's pretty obvious is the characteristic function of u plus the Q function of u equals 1. Everybody on that? Now here's the interesting thing. In your calculators, take a moment and see, because I'm about to do, I want to do just a couple examples of this. Show you. I'm going to do it with the Q function. It's the one I want. Either one will get you where you're going, Q or the characteristic. If you have either tables of that information or on your calculator you have some way of doing it, you can get any of the probabilities we need if it's a Gaussian random variable. So now, when I take a look at this, you can write this down. The actual Q function of u, this is the Q function of u, which is equal to the integral from u to infinity of 1 over the square root of 2 pi exp to the minus u squared over 2 du. This function is actually equal to 1/2 times ERFC. It's called a complementary error function, and then it's going to be a u over the square root of 2. Take a moment, see if you can see this function, ERFC, or ERFC, or ERF on your calculator. ERF is called the error function, ERROR. Can you see it? You got an error function of ERFC or ERF? Either one. Well, if you got both, you should have ERFC. It's a complementary error function. Huh? What do you have?
Inspire.
Anybody you got a laptop, right? Can you just look it up online, Inspire, where is the ERFC function? Do you have Inspire? Did you use this last time? ERFC?
We used tables.
Tables are pain, this is easy. I mean, I'm saying that, look, I had to use tables when I was in college, and I still have to occasionally. You know what I hate about it? It's so much easier just punching values in the calculator. Especially when you got these long, 20 pages you're turning to look at it. I'm not that inspired.
I'd have to program it in mind.
Yeah.
Can we do that?
I'm sure you can do it, but the thing about it is, I think you do have it inspired.
Or they might. I have the older ones. So
It's called either ERF, or matter of fact, you may have the normal distribution, so you don't need this. You do?
I'm pretty sure.
Yeah, we have the
What is
normal.
it called?
Normal distribution. If you got that, you know what the normal distribution is? That's this.
You go to menus.
Just look at the definition of normal
You go
distribution.
to distributions. Be it normal PDF.
Oh, wait, we got an inverse F. Is that what we were looking for?
No, hold on. I'm not sure. Just listen for a second. The technical definition of the normal distribution, f of x itself, implies that you have the standard deviation and the mean. Just listen. It is assuming Gaussian. So there'll be three arguments here. Y'all hear me? It'll be like x, comma, x bar, comma, sigma. Or I believe it's that order.
Could X bar be U?
Well, yeah, you could, if that, what's the first term?
X value.
And then u, that would be the mean value. And then what's the next term? That's it. That's it.
Yeah, we have.
Yeah, but I don't want to confuse you. The mu here means something different, all right? It's technically this, but that way, it's just distribution function, or is it?
It's normal PDF.
No, that's the probability density function, isn't it? Not the. Let's see. Just do me this favor, and we'll find out in a second. So this technically is the integral from minus infinity to the value of x of 1 over. Tell me if you've got this. This one. 2 pi, and I'll tell you why. Times sigma exp minus the quantity of x minus x bar squared over 2 sigma squared dx. This should be the definition of the normal distribution function. Distribution function. Now, how do we know it? Go ahead and just type this in. Tell me what this is. F of 5, comma 0, comma 0.1. That should be 1. Tell me what you get. What? Say again?
5.405 e to the negative 5.2.
E to the minus 500. You know what you got there? You got the probability density function. Now do this. Tell me what the value is of this. 0, 0, 1. That should be 1 over the square root of 2 pi, if that's the probability density function. And I think it is. Somebody's going to have to tell me what 1 over the square root of 2 pi is. What'd you get?
I got 0.39.
So tell me what 1 over the square root of 2 pi is.
Same thing.
You got the probability density function. All right. You need the distribution function, not the PDF. It would be the integral of that. I know you have it. I just don't know where it is.
So we just do the integral and then that function inside the integral?
Well, yeah, but you've got already that defined in your calculators. That's the whole idea is the distribution function, or just look up normal.
Inverse
What?
We have an inverse.
Try an inverse normal. All right, that's probably, which is kind of crazy. Inverse normal.
Yeah, that's negative.
What is?
0, 0, 1 for the inverse normal.
Is negative infinity? Should be 1/2. This right here says, if I want the probability, it's less than or equal to 0, with an average value of 0. So half the curve is below, half above. And a standard deviation of 1, it should be 1/2 if you got the right value, but you don't, obviously.
It's what the CDF function does.
Oh, is that cumulative distribution function?
Yeah.
All right, so y'all hear, is that the Inspiron? Y'all hear him? So what you can do, which makes a whole lot of sense, is you can say this function itself is called a C, on your calculator, C, is it CDF?
Is it normal or T?
Norm CDF.
What is it? All right, normal CDF. I want to make sure you got this normal CDF. You'll have something like this, but I'll show you a trick too that I use. And the first value will be the actual, what the random variable is less than or equal to. The second value will be the mean value, I believe. And the third value would be the standard deviation, not the variance, standard deviation. Y'all with me?
We have like a lower bound and upper bound, and then.
For what? That's if, hold it. You have a lower bound and upper bound for that?
Yeah.
Yeah, but the upper bound is just
Hold it.
X.
Wait, what's, is the lower bound defined or
Yeah,
undefined?
it's negative.
It can be anything.
Or it can be, but it automatically.
You can, does it default to negative infinity?
Yeah.
All right, if you don't have negative infinity, it's even better, you know why? Because now, if you defaults to negative infinity, it's fine. But if it doesn't, just put, if you want the probability between two values, lower and upper value, just make sure you enter the mean and standard deviation correctly.
When you do the 5, 0, 1 that you said earlier, it does equal 1. The
Better.
lower bound is negative infinity.
Better. All right. Yeah, that, good. Now you can play with your calculators. I'm going to give you problems, but I'm basically out of time. I'm just going to tell you this. This Q function, this is the thing I was messing with. Because I thought, I don't really know your calculators. So the definition of the Q function here, just listen to me and I'm going to tell you this. And Cameron, this might help you because you got the HP. I'm just going to tell you this. See this Q function right here? By definition, it's there. It's also equal to this. Q of U itself is just 1 over 2, and then it's going to be the complementary error function. And the argument will be U over the square root of 2. We'll do problems about that. But that will get you to 2. And I know ERFC was a more common function years ago. Now I got to get you quiz. So spread out all over.